Going to talk about increasing and decreasing functions. We kind of introduced it yesterday, but I want to rediscuss a little bit more, and then move into basically a result of recognizing where functions are increasing and decreasing. Okay? So here it says f is increasing on an interval I if f of x sub 1 is less than f of x sub 2 whenever x sub 1 is less than x sub 2 and I. All right, if we read that for the first time, maybe we don't have pictures. It's kind of maybe hard to deal with. And my suggestion to you as you go through other math courses, when you get something like this, try to draw pictures. Okay, try to go statement by statement. Okay, don't look at that whole thing and say, I'm going to try to figure out that whole thing at once together. Break it up into chunks. Okay, when it talks about interval I, all it means with interval I here is that between my x1 and x2, that's my interval I. Okay, generally speaking, it says if f of x sub 1 is less than f of x sub 2. So what that tells me, remember, f of x sub 1, that's function notation to provide us an output value, right? That's our y value, okay? So it's saying f of x sub 1. So it's saying this y value right there is less than that y value right there. Does that make sense to everybody? The y value produced by f of x sub 1 is less than the y value produced at f of x sub 2, okay? If that's the case, when x sub 1 is less than x sub 2. So when my first input is to the left of my second input. Does that make sense? Okay. Because if those were flipped, it would change the behavior of the graph. Okay. So we gotta understand that, and especially in both these actually, that we're kind of evaluating left to right on the x-axis. Okay. So if we get results for y values in which this first y value is less than the second y value, then that means the only way that I go from the first y value to the second one is to climb, right? To increase. So my function is increasing. When it's decreasing, you just see the different behavior here. You see the inequality flip, okay? So now this y value is greater than that y value, okay? So now because of that, because the first x value produced a y value that is larger than the second x value produced, therefore the function is decreasing, okay? Now the idea is that we want to make sure that that interval x1 to x2, that there's only one behavior happening in between that interval, okay? So for instance, I would not look at this and say that, if this is x sub 1, so this would be my f of x sub 1, right? Okay? And then come over here and say, well, this is x sub 2, because now in that interval, that's being f of x sub 2, okay? In this interval, you see how we start to increase and we decrease, all right? So that's a problem. What we want to do is we want to make sure that these two things are very close to one another, so there's only one behavior occurring, okay? When that's the case, then also we can decide whether it's increasing or decreasing. The next thing to do then would be, okay, let's move these points a little bit more. So we now use different inputs of x1 and x2. Maybe we call them x3 and x4. I don't care. It shouldn't matter. But now would we see the same behavior? Does that make sense? And ultimately the idea, guys, is that these points should be very, 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 very close to one another. And we continue to do that check. Is this point y value larger than this point's y value? And I keep doing that systematically until I get to a point where I can say, no, they're not. And then the behavior's changed. And then it starts maybe decreasing. Does that make sense? So that's the idea of increasing or decreasing. Graphically speaking, guys, it's not hard. Okay? You're going to see questions that look like this. Okay? And this is just the function. The function 12x squared plus 4x cubed minus 3x to the fourth. Okay? And they ask us to find the domain and range. Pretty much everything we do graphically, guys, throughout the course, one of the first things to do is to find domain and range. That's why quiz after quiz after quiz after quiz to get you focus on that and realize that that's an important task. So you're going to find the domain and range of this thing. Then it wants us to find the intervals on which f is increasing and on which f is decreasing. So domain and range, finding the domain, okay? If we look at this thing, look at the function, look at the rule up there, 12x squared plus 4x cubed minus 3x to the fourth. What kind of function is that? Okay, so f of x equals 12x squared plus 4x cubed minus 3x to the fourth. If we have exponents that are all integers, there's no division, okay? There's no roots or anything like that. That's why the exponents are integers, the positive integers. That thing's a polynomial, right? Okay? What is the domain of any polynomial we ever come across? All real numbers, okay? So the domain for this one's all real numbers. Looking at the graph, you can maybe interpret that. Now I should probably put arrows on there to really make sure that we understand that, but all real numbers is our domain, okay? If I put negative infinity, positive infinity, that's fine. All right, so the range, okay? So I start my range, I make a horizontal line at the bottom of my graph, right? What's the first value at the bottom of my graph that my horizontal line would come in contact with? Negative infinity, okay? And when I move that horizontal line up, so this is my horizontal line, first one to touch it, you said negative infinity, I keep moving it up. Are there any problems? Nope. Okay, and what's the last y value I come across? 32. So my range would be negative infinity to 32, inclusive with 32. Yes?
Wait, how come it's not negative infinity if the arrow there?
Say again?
How come it's not infinity? Infinity to 32?
Because these values down here are negative though, right?
Okay.
So when that goes down, it'll keep going down to negative infinity. All right, so now it asks for the intervals on which this thing is increasing or decreasing, okay? So every time they ask you questions about increasing or decreasing, your solution or your answer is going to be x values, okay? So we're going to be providing x values in which the y values are showing a behavior of increasing or the y values are showing a behavior of decreasing. Does that make sense to everybody? Okay? So I'm going to write, this is usually the way I do it. I'm not saying this is right or wrong, I just think it's the most obvious and you don't miss anything on accident when you do this. You don't miss an interval. If I start left to right and I just put myself on the graph and I start moving along that graph, and when I highlight these y values, what are those y values doing? They're increasing, right? Getting bigger and bigger, okay? Until I get to that red dot, right? Because after that red dot, what happens? Yeah, you start going down, right? You start seeing that your y values are smaller than, after that red dot, your y values are smaller than that 5, okay? So I'm increasing, the first x value that I would be increasing with would be negative infinity. In the place of the stops increasing at what value? Negative 1, right? Okay. So we're increasing from negative infinity to negative 1. Okay. The place in which it stops increasing. Okay. That point B. We don't include that in our increase or decrease. All right, because it's got really a different behavior. Because to the left of that point we're increasing, to the right of that point we're decreasing. So at that point we're kind of static. Does that make sense? We're not doing either thing. So there we are increasing. Let me write that in blue instead of black real quick so we can color code this stuff. So negative infinity to negative 1. And now I'm going to continue on my graph. But now what are my y values doing as I continue on my graph? Getting smaller, right? Okay. So now I'm going to look for the x values. I'm going to write the x values that I just saw that my graph was decreasing for, right? Would you guys agree that those x values are between negative 1 and positive, or sorry, negative 1 and 0? So decreasing from negative 1 to 0. And then after that, what's the graph start doing again? Starts increasing again, right? Increase, increase, increase. Keep doing that until I get to that point right there. So what were the x values that blue curve, portion of the curve, is increasing for?
0 to 2.
0 to 2. Okay. And then, so you see how I'm kind of bouncing back and up and forth, up and down between these two things, right? And then afterwards, what are you doing? Decreasing. Does it ever stop decreasing? No. So our final decrease would be from 2 to infinity. Okay. Now these intervals, both of them are increases. Does that make sense? So I can't just have them this way. I've got to union them and say that within both of those, I am increasing, and I am decreasing in both those. So union those. Okay. So the notation for showing where we're increasing and decreasing is the same as what we show for our notation for domains and ranges, right? Okay. So hopefully that practice that we've been doing with writing interval notation, all that kind of stuff, can carry over, and we've gotten good at it, and we can easily identify these intervals. Okay. So remember, these are x values for which y values are displaying, this is terrible writing, displaying such behaviors. And I think it's important because a lot of people will write these things down here and not be sure what they mean. Okay, those are the x values in which my function is increasing, and those are the x values in which my function is decreasing. And we make that argument, we make the decision of whether it's increasing or decreasing based off the y values, right? Okay? So that's very important. A lot of times I get people to write down the y values that are increasing and decreasing. Does that make sense? That's not what we're doing. Okay? Kind of the y values, when we compare the y values, it just tells me yes, it's increasing, or no, it's not increasing and it's decreasing. And then I write the x values in which that happens for. Okay? So it's very important that we can do that. We'll see a couple examples throughout the rest of the slideshow that asks us to do that. But that's the thing, guys, is now that we know how to find domains and ranges graphically, we now know how to find intervals of increasing and decreasing. Pretty much every time that we see a function now, those are going to be the first couple things they ask us. Okay? Because we're really trying to, when we provide a function in front of you or a graph in front of you, analyze that, figure out everything I know about it. Okay? Because the more I know about it, the better I can use it, the better I can analyze it, the better I can apply it to something else. Okay? So there are a couple places here that are very important to us. If we look at that -1, that -1 got kicked out. Okay, and all our intervals that we used it, right here it got kicked out, and right there it got kicked out, right? And you see that on the left-hand side of -1 we were increasing, but on the right-hand side of -1 we're decreasing. So then at -1 we weren't doing either of those things, right? Okay. So at -1, that point right there is a critical point. Okay, and a lot of times that's what we call them, is critical points, especially when we get to calculus. We'll use that phrase a lot. Same thing happens here. 0. Did 0 get kicked out there and there? Okay. Damn it! Woo! Nightmares. Okay. So 0 needs to be kicked out. Okay. And we also saw that up here at 2, that got kicked out. And each one of those, they share similar relationships, right? They share an idea or a concept that at those points, we either went from increasing to decreasing or decreasing to increasing, right? There was a change in behavior of the y values. That change in behavior of y values, those points are considered or called maximums or minimums, okay? A lot of times collectively they're called extremums, okay? Or extreme values. So let's discuss that stuff a little bit. We'll go back on I showed the last class how to do this stuff on their calculator. We'll go back towards the end and show you how to get that graph on your calculator if you're using a TIA 3 or A4, how to manipulate that. Okay. The local maximum minimum values of a function. And you just define them here. It says the plural is maxima and minima. You'll see the word extremum and extremos. They're just referring to all of your maximal values, all your minimum values. Okay? But what the first one here says, the function value f of a is a local maximum of f if f of a is greater than or equal to f of x when x is near a. Okay? This thing where it says x is near a, that's kind of a vague phrase. And anytime that we worked in geometry, we talked about doing proofs and writing definitions and that kind of stuff, that we wanted to avoid vague words, right? Because right now I might be near to Dominic, right? Still maybe near to him. Now near to him, but maybe now I'm not near to him, right? So I'm not near, but now I'm near. Where in between those two spots was the cutoff for being near or not near, right? So that's kind of a vague word, not a great word. But when we look at this down here, okay, the idea is that when we say near A, is that we're on some open interval, okay, that is very close to A, and we're going to try. Ultimately, what happens, guys, is we try to get that distance between A and X to be infinitely small, okay, and that makes things a little bit easier for us. But kind of show you a graphical understanding of what this definition says. I think, again, this is another definition, another math definition, that if you were just provided this without any pictures or anything like that, at your level, it's kind of hard to interpret, kind of hard to understand, okay? So I'm going to give you a picture. And in the picture, I think, if we break this down piece by piece, it makes it real obvious what they're saying here. So let me look at this picture here. All right, so what they're saying is that, we had a maximum. That's what we were talking about. So let's say this is our maximum point right there. And if I'm on my x-axis, they're saying that x value would be a. Does that make sense to everybody? This y value here would be f of a. So this ordered pair is called a f of a. They're saying that this is a maximum, okay? F of a is your maximum value. Your y value is your maximum value, okay? If f of a is greater than or equal to f of x when x is near a, okay? When we get to calculus, we'll talk about limits, and maybe we change that definition a little bit. We'd say when, maybe the limit as x minus a approaches 0, okay? As the distance between these two things gets very, very small, okay? Right now, I don't think we have enough knowledge about that to be able to do that. What they're saying, though, guys, is that our x values are going to be close to a. Maybe that's what I'm saying there. Maybe those are near values that are values that are near a. Okay? And would you guys agree that each one of these is an x value? Okay? Well, if I go and look at the respective y values, okay, that y value, maybe I call that f of x sub 1. So maybe this one here is x1. Maybe this one here, let's call it x sub 0. So the y value there would be f of x sub 0. Maybe this y value here is f of x2, okay? So we get that idea, right? We're seeing these x values are going to produce these y values, correct? Would you guys agree that f of a is greater than or equal to any of those f of x's? Yeah. So what's that tell me then? Because that y value is larger than all the other y values that are around it, it tells me that thing's a local maximum, okay? Now it's a local maximum because think about this. If I'm not near a, let's say x is over here, say I have x sub 5 over here, that y value, f of x, is much larger now than this y value of f of a, right? Does that make sense? Because we've now kind of destroyed that idea that x was near a, all right? So we want to make sure that is something we're interested with. That's how we define what a maximum is. Okay. Same thing happens with a minimum. Essentially, let's say that maybe point B is here. Okay, or coordinate B. Then that would be f of B. Would you guys agree that that y value there of f of B is smaller than any of these red values that I highlight there? That would be respective f of x's. Okay? So if that's something we can decide, and we can determine using that rule, using that definition, we can identify maximums and minimums pretty easily. Okay? Now the idea is, collectively, when I look at a maximum or minimum, okay, let's say that this is my graph. And let's say it terminates there and there. Okay, so we've got endpoints here. Would you guys agree that this is the smallest y value on the entire graph? Do you agree with that? Okay. Would you guys agree that this is a smallest y value for the points that are around it or near it? Okay. Would you guys agree that that point right there is the largest for points that are around it? So points that are around it, and we're using the word local. And what would this one be? Yeah, that would be the largest y value for the whole thing, right? Put all in parentheses here. Okay. So those are all critical points. They're all useful points, and they're all maximums or minimums. Okay. This one here, let's talk about these ones that we talked about with f of a and f of b. Essentially, guys, when we're deciding that that is the largest y value for the points that are around it, we're basically taking our view screen and we're just going to focus in on that part of the graph. So the rest of the graph doesn't exist. Does that make sense? We just zoom in on that. And within that aspect of that portion of the graph, we can say that's a maximum, right? Okay. But then when we zoom back out, we understand, well, that's not the whole maximum or the largest maximum, and it might not even be the only maximum. Okay? So what we do is we call that one a local max. Okay? Because it's largest for the things that are around it, right? In its locality, in its little neighborhood, it's the largest one. Again, for this one down here, okay, if I look at that little neighborhood, okay, that one is also I guess not also, but it's a local, but minimum now, right? Okay. Now, even if I look at this one, okay, let's look at this one here in its neighborhood. Would you guys agree, if I look at that neighborhood, and that is a local maximum for that little neighborhood, that little window, but compare that to any other local maximums up there, is that local maximum, this one right here, larger than that local maximum? So because that's occurring, we call this one cursor died, call it an absolute maximum. Sometimes refer instead of absolute, sometimes they'll say global. Okay, meaning the entire curve. Okay, and this one here would be an absolute, minimum, or a global minimum. And basically, when we see those adjectives, local tells me that it's the largest y value or smallest y value in that vicinity, in that area. Okay. But when I see the word absolute or global in front of minimum or maximum, now it tells me it's the largest y value or smallest y value on the entire curve. Does that make sense to everybody? Okay. So we'll ask you questions like that. We'll give you a picture and say, okay, go through and identify all the maximums and minimums. Identify which ones are local. Identify which ones are max or global and absolute. Okay. So hopefully that's not too difficult to do. Okay. But what is the relationship of where every local maximum and every local minimum occurs? It's at the place where increasing and decreasing changes, right? Okay? It's that static point, which is doing neither of those things. And why is this important? This is very important to us, guys, for the reason, let's see if I can make a quick graph here for us. Let's actually go back to this graph here, 12 x squared. All right, so we got that graph, right? I'm going to ask for this thing to find a tangent, I think. Point line. Okay, good. All right, so trying to show you a little bit about what we're doing and why we learn this stuff, so we can deal with some calculus stuff. Okay, one of the main things in calculus that we're interested in is the slope of this curve at different x values. So if I look at this point A, let's put its ordered pair up here. Okay, maybe I'm interested in the slope at negative 1.35 for this curve. Okay, well, if I'm able to find that line, the equation of that line, the slope of that line is exactly the same at that point as the slope of the curve at that point. Does that make sense? Okay, and we go through a process called differentiation to be able to do that, and we've already seen some components of that process in this course. But that changes. The slope changes all the time, because look at that line right there. And even if I ask GeoGebra to come up with the slope of this line, you can see that right there it gives me, it's kind of messy, it gives me a slope of 18 right there. But as I move, does that slope change? Okay, so what happens, what's my slope become right there? 0, right? Okay, let me get the grid off here. Let's get the axes. I don't even care about the numbers. All right, so if I'm looking at this point, we see our slope. Our slope right now is positive, right? Becomes 0 right, stop right there. And then my slope becomes what? Negative. So when my slope is negative, what's my graph doing? Decreasing. When it's 0, when my slope is 0, what's my graph doing, or what am I finding there when I have a slope of 0? Change the direction, right? Change from increasing to decreasing, or decreasing to increasing, so that's one of those maximum or minimum points, right? And then the slope being positive again, okay? And we'll get back up here, and there we get, eventually we see it that we got a 0 slope again, okay, at that maximum. So we're going to be interested in calculus to be able to analyze those slopes in that line, that segment, but it has a direct link to what we're doing right now. So the maximum minimums that we're dealing with right now, and the way we find them right now is going to be kind of a mathematical, algebraically, it's going to be kind of a messy process sometimes. Okay, you know how to do it with quadratics, okay? But with cubics and quartics and quintics and stuff like that, it's very hard to find those maximum minimums mathematically. Okay, calculus does it for us. Calculus finds it very quickly, actually. Okay, you're going to see in your homework, guys, they're going to ask you some questions. It's not due until Thursday, so we talk about some of it tomorrow. But you're going to see questions like this. Okay, where they ask you, can you find g of -4? Okay, well, this is stuff we've been doing for pretty much the duration of the course so far. G of negative 4, okay, that's my x value, right? That's my input. So I go find negative 4 as my input. And now what's the output that I get back? Be 4, right? No, it is 5. Man. So, thank you. That'll be 5. So now I go find g of negative 2, right? And now that one would be 4. Find g of 0 would be 0. G of 2, 3. G of 4, 2 again. What if I said g of 2? Okay, we already did. G of 2 is 3. We see it in I didn't talk about the discrepancy there. One's open, one's closed, right? We got to choose the closed one. Okay. The next thing they ask you, what's the domain? Have we been doing that? They'll ask you what's the range. Have we been doing that? Yeah. And now, basically, the increasing and decreasing is to take that domain that we've already found and look at the portion of it in which we're decreasing for the y values, and look at the portion of it in which we're increasing for the y values. So that allows us to find the increasing and decreasing. And then once you find those, you should automatically be able to find the maximums from that information. Okay? So we'll do a couple of those tomorrow. My hope tomorrow is also to get into average rate of change, which if you remember the way we defined slope back in Algebra 1, that's all that is. Okay? So we'll deal with slope a little bit tomorrow and average rate of change after we pick up with some of these examples.